Okay. Yeah, thank you very much. I'm very sorry that I couldn't go in person. And yeah, thank you for the accommodation that allow me to speak online. Uh, so this talk is based on joint work with Ilya Chevyrev, who is in the audience, and it's based on this recent paper that we posted in February with the same title. And this is part one of the talk, and Ilya will give the second part of this talk. So let's just quickly recall the physics background, the context. So in physics, usually very often we define physics model by action functional called S here, where phi is some sort of field. Well, when we quantize such a physics model, we usually formulate this quantization in terms of a functional integral with respect to this formal measure, which is exponential of action functional. There's another formulation, right, which is called stochastic quantization. This is a link between quantum field theory and stochastic PDE. So in stochastic quantization, we look at this dynamic, which is the gradient flow perturbed by a space-time wide noise. This dynamic is such that this formal invariant measure is formally invariant. It's invariant under this dynamic. So this is the setting of this talk. And in this talk, the action functional is going to be the Yang-Mills action, and it's action functional for field A, which is the algebra value one form. I'm going to define this more precisely later. So for this talk, I'm going to first recall the definition of Yang-Mills model, namely I just defined precisely the action functional S. And then I'll introduce a class of so-called lattice Yang-Mills models, also called the lattice gauge theories. These models are well-defined models on lattice, and they share the same sort of symmetry called gauge symmetry as a continuum lattice model. Okay, and then I'll quickly recall the earlier work with AJ, Ilya, and Martin on the construction of the stochastic quantization of Yang-Mills in 2D and 3D. And then I'll state the main result in this paper with Ilya, where we prove the convergence of the dynamics for this class of lattice Yang-Mills models to continuum limit. And we can identify this continuum limit as the dynamic we constructed earlier with AJ and Martin. So this part we can identify the limit. So this can be interpreted as a universality result, right? So this shows that this dynamic reconstructing continuum is universal. And then yeah, so this is in 2 dimension. And finally, in 2 dimension, we can show that the 2-dimensional Yang-Mills measure is a unique invariant measure for this dynamic. This result about the invariant measure actually relies on the discrete approximation, because on lattice we can explicitly check the measure is invariant and then we pass the limit. So in my talk, I focus on this item 4, and item 5 and 6 will be in Ilya's talk. Okay, so Yang-Mills model, Martin already defined in his talk, and let me just repeat with the same notation. In this model, we fix a Lie group, a compact Lie group called capital G, and the Lie algebra for this Lie group, which is little g. And then imagine that we have a underlying space of dimension d, such like a d-dimensional torus. And then the Yang-Mills field, right, living on this d-dimensional space, is a one form, so it has d components, and each component takes value in the Lie algebra. So for any x, AIX is element in the Lie algebra. So this is called the Lie algebra valued one form. The Yang-Mills action, right, which define the Yang-Mills model, is the L2 of the so-called curvature. And the curvature is a two form where the ij component is given by the curl of A, that is the curl, plus the Lie bracket of AI and AJ. You can check this as anti-commutative in IJ, so this is one form. So it's a two form. And the L2 of this just means, okay, so as a two form, you just take the square sum over all the IJs. And okay, it take a value in the Lie algebra, so you just fix the inner product in Lie algebra and do L2 over that. And finally, you just do L2 integral over the underlying space. That's what I mean by L2. Well, actually, so this is the definition of Yang-Mills model. Actually, if you pretend everything's scalar, right, pretend A is just a scalar function, then the F is like something like a dA, right? The bracket is just 0. And then this is just the, integral of dA squared, which corresponds to the heat equation. So this is a kind of, non-abelian or non-commutative generalization of that. Okay, so so there's a gauge symmetry which says if you take any Lie group valued function g and do this transformation, this is called the gauge transformation, it maps A to a new Lie algebra valued one form. Right, so just take conjugate of A and then this is also Lie algebra valued function. And this transformation will leave the action invariant. This is like a half-page check calculation. So let me emphasize this is actually infinite-dimensional symmetry because this is true for any function g, right? So you can take any function. So this is infinite-dimensional symmetry. The quantum Yang-Mills model is given by this formal measure e to the s. This is again complete formal measure. Okay, so lattice Yang-Mills model is a class of well-defined models on the lattice. They preserve the gauge symmetry. So it's defined in the following way. Imagine this is a d-dimensional lattice. And okay, so now our field, you should think of the field as a discrete analog of one form, which has d components. And therefore, we define the fields on the edges instead of lattice vertices, because edges also have d components. So for each edge xy, we assign a element of the Lie group uxy. So this is our field. Okay, so the measure. Okay, so basically we have a collection of Lie group elements living on all the edges, and now we define the measure over such fields. It's an exponential of a discrete Yang-Mills action product du. So du is just Haar measure on the Lie group. It's just a translation invariant measure on the Lie group. And now the action is defined by sum over all the plaquette, the so-called plaquette. Plaquette just means a unit square consisting of 4 vertices x, y, z, w, right, in the picture P here. And then for each plaquette P, we look at the product of all the 4 Lie group elements around this plaquette. So each edge we have a uxy times uyz and so on. This is also an element of Lie group. And then I have this function which maps Lie group to real numbers. This function little s is conjugate invariant. Right, so now you have a number, so this s this action functional, it give you a real number. So this is the measure. Okay, so if compare with other lattice models like Ising model, the spins here take a value in the Lie group, and this is the kind of nearest neighbor interaction. So maybe you should really think of this as a, or maybe the log of this as a discrete analog of curvature, because this product is like you curl around this plaquette. So so just like in the curvature, you have a curl. Okay, so Now this model also has a gauge symmetry, gauge invariant, namely, if we take any g-valued function little g, now the function g lives on the vertices. Okay, so then I do this transformation. This transformation looks like a conjugate, but it's not, because I multiply uxy on the left by gx and on the right by gy inverse. So xy are different. Now we can explicitly check that this is, this action functional is invariant, because it's very simple, right? So here you multiply uxy by gy inverse on the right, and then you multiply uyz by gy on the left. So the gy inverse gy here cancel, and similarly cancel here and cancel here, right? So what remains is the gx on the left and the gx inverse on the right. But since we assume S is conjugate invariant, so this whole thing is invariant. By the way, S also assumed to be invariant under inverse. Therefore, it doesn't matter if you go counterclockwise or clockwise. Okay. So this is really a class of models, because this function S can be arbitrary. Let me give you some examples about this function S. Wilson action, here I assume the Lie group is a matrix group, such as SUN, and then you just take a trace. Okay, so that's called Wilson model. And for VLAN model, it's just log of heat kernel on the Lie group. And then there is so-called Manton model, which you kind of fix a metric on the Lie group, and you take the distance from the identity, square that. Okay, so these are some famous examples. Now, for the rest of the talk, we're going to focus on class of such models, and we prove as a lattice spacing go to 0, the corresponding dynamic converge, right? So let's put some assumption on the function S here. We assume that the after you rescale the lattice spacing to epsilon, the function has the following form. It's epsilon to the -2, which is a well-known scaling for Yang-Mills, for lattice Yang-Mills to presumably to convert to limit, right? In dimension d, this is d minus 4. So we're in 2 dimension, and then times the distance from the identity square, and this term is actually just the Manton action, and then plus a remainder r, which satisfy the following assumption. So this assumption looks technical, and it takes some time to appreciate maybe, but it just says that if you, so there exists some linear maps, E1, E2, which are uniform bounded by, in epsilon, such that if you pull back this function, right, so you compose with exponential map, then this function is a function on Lie algebra, and then the gradient of that at Lie algebra element x is given by such linear operators plus some big O errors. So this this apparently technical assumption is such that all these assumptions, all these models, Wilson, VLAN, and so on, they satisfy this assumption. Okay, this you can check because okay, as a matter of fact, they look quite different, but they're not so different, because if you look at the Wilson example, this is also some sort of distance from identity, but you kind of measure distance in a linear way in some sense. And also in the VLAN model, if you pretend this is the usual heat kernel, then this is something like a distance square. So they all look like maybe some perturbation of Manton. And this assumption eventually is also such that when we look at the corresponding terms in the stochastic PDE, they vanish in the right way, and that's why this assumption is about the gradient of this function. So because it's a gradient which appears in the dynamic. Now, with this class of models, we look at their dynamic. So dynamic of lattice Yang-Mills models are defined in a similar way, right? So it's just a gradient of this action functional, where the gradient is a gradient with respect to a fixed metric on the Lie group, and this noise is a Lie group valued Brownian motion, right? So for each edge, we have independent Brownian motion on the Lie group. Okay, so this is a diffusion. This is just a system SDE on the state space. The state space is a product Lie group. It's just a product Lie group over all the edges, right? And if the lattice is finite lattice, just really a finite dimensional SDE. So maybe I should give you a simple example, although we never use this example later, okay? Just to show you there's some concrete form for this equation. For example, if we take the Wilson action where the Lie group is just a unitary group, then you can actually write this gradient term in a very explicit, very simple form, where you look at the evolution of the U variable at this edge E, right? And then the dynamic for UE involves the neighboring U's, right? The neighboring fields. So here in 2 dimension, E is there are 2 plaquettes P and P bar adjacent to E, and then the UP just means the product of U's along the around the plaquette, the product of 4 U's here. So this is basically the drift. Okay, so that's a very simple equation. Okay, so this noise is the W is the Lie algebra valued noise, but I'll come back to this later. So my point is just sometimes you can write very concrete SDE, and you can even with a fixed lattice spacing, right? Even you look at a unit lattice, you can study many questions about this SDE. For example, you can study exponential ergodicity, or you can prove some sort of log Sobolev, or prove derive some sort of lattice master loop equation for discrete Yang-Mills using this SDE, and so on. Okay, so we have some papers with Scott Smith and Rong Chan, Xiang Chan in the audience on such result. But I don't want to talk about this in the talk. What we are going to do is to take continuum limit. Okay. We're going to send the lattice spacing to 0. Okay, so let's first recall the limiting object. This is, Martin also described our result. This is earlier result with Martin and AJ and Ilya, where we just look at the continuum, right? Forget about lattice. So in continuum, we can write down the stochastic quantization explicitly, this in terms of this SPDE. It's a heat equation plus Lie bracket, right? This term basically A times dA, and then there's a cubic term AJ AI. And this because Ci is an independent, it's a collection of independently algebra valued Y noises. The red term here is a renormalization term, with renormalization comes C times A. Okay, so in this paper, we show that the equation is locally well posed. But not only that, we prove that with a specific choice of this renormalization, as Martin said, the dynamic has a gauge covariance property. Let me just repeat what this means. Here's a picture where my screen is the infinite dimensional space, all the fields A, right? And then in the space of fields A, we have an infinite dimensional gauge group acting on this, and all these curves are orbits under the gauge group, under the gauge group action. So each curve just means the equivalent gauge equivalent class of fields. Gauge covariance property means that if I start with, at time t, if I start with 2 initial conditions here and here, they are gauge equivalent. and then I run this dynamic from here and also from here, then at positive time t, there are, the two solutions at t are still gauge equivalent in law. This means the dynamic doesn't really depend on which representative element you start from this equivalent class, from this orbit. In other words, this dynamic is really, a dynamic over the space of gauge orbits, or over the quotient space. Okay, so what we prove is that, you can do a finite shift of this constant c and get different solutions. So we have a one parameter family of solutions, but among this one parameter family, there's a special one which satisfies this gauge covariance property. Okay, and by the way, as Martin said, there's the Turk term, because you just look at this is kind of degenerate, not a Laplacian, but the Turk term, makes this linear part into a Laplacian, and it doesn't matter because the Turk term is a drift with the parallel with the gauge orbit, so it, doesn't change the gauge equivalence class. Okay, this paper with AJ, Ilya, and Martin raised two questions. The first is whether this dynamic, this Markov process on the space of gauge orbits, in some sense universal, right? Whether this is universal limit of all the dynamics for all those, the dynamics, all those lattice gauge theories. The second question is about the invariant measure. In fact, in 80s and 90s, the two-dimensional Yang-Mills measure was constructed in terms of random holonomies by a group of people, because two-dimensional Yang-Mills has some special integrable structure. It's subdivision invariance and so on. So it's easy to, it's not hard. It's possible to construct. So the question is this two-dimensional Yang-Mills measure really the invariant measure for our dynamic? In this new paper with Ilya, we answer yes to both questions in two dimension, on two-dimensional lattice, two-dimensional torus. So I'll focus on the first question, and Ilya will talk about the invariant measure. Okay, so the theorem is that for all those, lattice, the class of lattice Yang-Mills models, which satisfy the assumption I described later, right? So just the just this assumption. Let me just go back. It's just the distance from identity square plus error with some assumption error. And by the way, you can check this, the Lie group distance from the identity square is the same as you just take the log of this u, right? So this is a Lie algebra valued function square that. Okay, so it's just the same. So as long as this action functional satisfy this assumption, which is still quite general, then as lattice spacing go to 0, the log of the discrete dynamic converge to the dynamic that we construct with AJ, Ilya, and Martin. Okay, so how do we show convergence of discrete dynamic to continuum limit? Well, okay, so let's just recall this is our discrete dynamic, right? The gradient of the action, but then we also put a discrete analog of the Turk term. This fancy B is a Lie group valued Brownian motion. There is a well-known fact for Lie group valued Brownian motion, which says you can actually rewrite the Lie group valued Brownian motion in terms of Lie algebra valued Brownian motion. This W takes value in the algebra, where the this U circle is a Stonovich product. Okay, this is just well known in stochastic analysis on Lie group. Now for this dynamic, how do we show convergence to the limiting SPD, right? Of course, the general idea is to first rewrite this discrete dynamic in terms of some sort of finite difference equation, which already looks closer to the limiting SPD plus error terms, and then we try to bound error terms. For example, this kind of general strategy also in the recent work by Hendrik Constantin and Apollo on Ising model converge to 543. It's always like that, right? So you try to rewrite the dynamics into a form which look closer to the SPD. But the trouble here, the difficulty here is that this dynamic actually looks quite far from the limiting SPD. For example, if you look at, let's go back. If you look at this equation, this SDE system, compare with this heat equation with nonlinear terms, they look quite different. So, so how do we actually? So the general, okay. So our strategy, okay. Maybe before I get to abstract, let me just show you it's possible to see that the linear terms we get from here is really Laplacian. Okay, at least we show the linear term is a heat equation. So let me just show you this. So recall that the discrete Yang-Mills action is is sum over all the plaquette, and then this is a function of the product of the four unitary 4D group valued variables, right? So you just multiply, this is edge E, you just multiply the four Lie group elements along this plaquette. So since we assume that the function S is approximately log X norm square, where the argument X here is a product of four guys. So basically we're taking the log of the product. And the so-called Baker-Capel-Hausdorff formula tells us that the log of this product is basically, okay, the linear order is the sum of the four A's, or all the A's are the algebra value elements, and then plus higher order correction terms, which are iterated Lie brackets of all these Lie algebra value elements. Okay, so the other terms here, they are not linear. They're quadratic and cubic and so on. Okay, so so in terms of this picture, if you look at the evolution, the dynamic for this edge E, then only two plaquettes are involved. Here, we have the sum of the four A's, right? So here the direction of the arrows matter because when you reverse the as my convention, when you reverse the direction of the arrow, then the A gets a negative sign. So this is the sum of the four A's and the sum of the other four A's in the other plaquette. Okay, so this is the linear order of this gradient. And similarly, you can also write down the linear order of the Turk term. It's just that you look at the, it's like a divergence at this point, right? This is the same edge. So you got a divergence here and minus that divergence here. And when you combine them, right, when you add up this, you see here the down arrow and up arrow, they kind of cancel. So what remains is these arrows. It's obviously Laplacian, right? It's just a sum of the four guys minus 4 times this. Okay. This is the linear order. However, the nonlinear terms, the nonlinear orders are much more non-trivial to derive. Our strategy to derive them is the following. So recall that there is the exponential map from Lie algebra to the Lie group. As long as you are just in a neighborhood of identity, this exponential map is a bijection, right? So our strategy is that we pull back all the structure. So this is where the dynamic lives. Okay. We're going to pull back all the structure from the Lie group to the Lie algebra using this exponential map, and then we just work with this Lie algebra right from the start, and then we'll just forget about Lie group. In particular, on the Lie group, we have a Riemannian metric, right? And we're going to pull back the Riemannian metric from the Lie group to the Lie algebra. And Now the Lie algebra was just a linear space. It has a metric which is just Euclidean metric. But now by pulling back the remaining metric from Lie group to Lie algebra, I'm making the Lie algebra into a Riemannian manifold. Okay, which has a metric which is different from the Euclidean metric on the Lie algebra. Now this means that exponential map is now isomorphic between the Lie algebra and the Lie group as two Riemannian manifolds, as long as we're in the neighborhood origin. Okay, and also we pull back the action here, right? The action is just a function, you just pull back that. And we also, take the gradient of the pullback action or the gradient with respect to the non-trivial Riemannian metric. And also we pull back the Turk term and noise from here to here. Okay. So let me show you a picture for this. This is my Lie algebra, and this is the Lie group. Okay, the product Lie group over all the edges, right, which is also a Lie group. And the exponential map maps the origin to identity, and it maps Lie algebra element A to e to the A. How do I pull back a Riemannian metric? Well, I look at two tangent vectors B and C at A. To define the pullback Riemannian metric, I just need to define the inner product between B and C, right? So the inner product defined in the following way: I push forward the tangent vector B and C using the exponential map to the to get the two tangent vectors of Lie group. Okay, and then I take the inner product of these two push forward tangent vectors, and that inner product is defined to be the inner product here. Okay, so how to push forward tangent vectors? Well, just for example, take a curve with this vector as a tangent vector, and then you just embed the curve to the right hand side and differentiate that curve, and then you get tangent vector. That's the push forward tangent vector. So essentially, it boils down to differentiating this exponential map. So, well, okay, it turns out that there's a formula to do this. The push forward of this tangent vector B is just equal to e to the A phi A, this operator phi A on B, where phi A is defined in the following way: that this is adjoint action by A. Okay, so this can be found from some Lie group theory textbook, for example. Okay, so the inner product between BC is given by this. Okay, and by the way, since I can choose the metric on the Lie group to be the bi-invariant metric, I can erase the e to the A here and replace the e to the A by identity. Okay, so in some sense, okay, so maybe, okay, so as you can see, if A here, if the base point A here turns out to be the origin 0, this is actually identity map. So in some sense, at 0 is the usual Euclidean metric, but away from 0, the Euclidean metric get twisted in some sense. Okay, what about the noise? Okay, so the pullback noise is also a drift, or also a tangent vector at this point A, such that the push forward of this tangent vector is given by the noise, right? This is the Stoyanovich product between the U, which is e to the A, times the Lie algebra valued Brownian motion. In other words, this pullback noise is given by the inverse of phi acting on the Lie algebra valued noise. Okay, so if you Taylor expand this operator phi, and after rescaling, after suitable rescaling, I denote this noise by Cassi, then the expansion for Z looks like this. It has the Cassi, which is the discrete Y noise, plus some correction terms here is epsilon times the multiplicative noise, like bracket A cos C. This has an epsilon, but it's still singular because in 2-dimension, the A has regularity slightly below 0, and the cos C is like -2. So the whole power counting for this is -1, and this is still slightly below 0. So these terms are still singular. And then the next order, you might think the power counting is positive, but it's actually more subtle than that, because in the spatial direction it's a lattice, but we didn't discretize the time. So in the time direction is still singular, and this product in the time direction should still be interpreted in terms of Stoyanovich product. So there's still some stochastic information that we need to encode in this term. Anyway, we can rewrite this whole thing here as additive noise plus some function f, right? The sum of all the terms times the A cos C. So I want to emphasize that in this equation we have additive noise, but also a multiplicative noise. Okay, so now after all the work, we can rewrite the discrete equation in the following form. These terms are the same form as the continuum Yang-Mills equation, right? So quadratic terms and cubic term, and plus the discrete Y noise. And then after this, there are many remainder terms. So all the remainder terms come from several different sources. For example, when we use the Baker-Campbell-Hausdorff formula, right, expand the log of products, we get remainder terms. And also we have, so in the noise, we have additive noise, C, but with also a multiplicative noise. This comes with epsilon. So that's why we call the remainder term. And there are some other remainder terms coming from the fact that we somehow enforce the drift to have this form, but it's not quite that, right? So there are some discrepancies which look like this. For example, epsilon times the Lie bracket of dA, where the two dAs might be evaluated at slightly different like neighboring points, or something like this. And also there's a remainder from our assumption on the action. Okay, so there are tons of remainder terms. A surprising fact which we prove is that it turns out that all these remainders will lead to a constant times AI in the limit. Okay, so these remainder terms, they don't simply vanish, although they come with epsilon, right? They're still singular, so they don't vanish. In the limit, they contribute to a very simple term, right? It's a term with very simple form, that's constant times A. Actually, more precisely, it's not just these remainder terms, because the remainder terms are so singular, they actually affect the renormalization of the main terms in the equation. Okay, so not just the remainder terms, but also their interaction with the main term in the equation. They all end up with this same renormalization term. Okay, so this is a result of detailed calculation and study of certain symmetries such as reflection symmetry or parity, studied calculated consolations and so on, to get this result. Okay, in particular, you might wonder why we have this funny decorations, little a here, and the funny derivative here. This is because, right, so let's say the a is a variable on horizontal edge, then the evolution of this variable depends on the vertical edge, but then this little a is like the average of the 4 neighboring vertical edges around the horizontal edge. So it's really, we really write these terms in a symmetric way. Also, this kind of partial derivative is defined to be kind of a centralized finite difference instead of just a naive forward derivative. In this way, we can preserve certain reflection symmetry and so on in order to get suitable cancellation and so on. Okay, so this is a subtle point. So maybe more specifically, we deal with the main terms and remaining terms in the following way. So for the main terms in the equation, there's a discrete framework regularity structure by Dirk Erhard and Martin. But we sort of extend this framework by introducing a few more ingredients. For example, so some of these terms here are non-local. And we introduce a shifting operator, which kind of shift the field to neighboring edges. And for experts, they behave like integration operator in regularity structure in some sense, right? We have to impose that they commute with reconstruction operator and so on. And since the multiplicative noise has this form, where we have this function epsilon times a, and again, I recall that in the time direction is still singular, but multiplying the lattice space in epsilon doesn't improve the time regularity. So somehow we should really encode some stochastic information here. So that's why we should view this epsilon as something abstract, like abstract operator working on the regularity structure level in order to do this. But okay, so this is similar with the earlier work of Martin and Jeremy Questel, but we have to do this on the lattice, and also we have to define the epsilon operator on the minimal sector of the regularity structure so that we don't produce too many new elements in the regularity structure in some sense. Okay, and then for the remainder terms, so all those tons of remainder terms we just categorize them into three regimes. The classical regime means you can just show this kind of error terms vanish in classical way, but then there is the Prado-Debouche regime where we should use the fact that the solution can be decomposed into a singular Gaussian plus the smoother remainder. And if these are Gaussian, right, look at the Gaussian part, then you can easily see that this part actually convert to a constant. Okay, that's how we get a constant times a in the limit. And by the way, for expert, maybe you wonder if we have a single derivative by parity, this constant is really zero or not, right? This depends on what derivative this is. It's just a forward derivative on the lattice. We don't have exact parity, so we should really be careful about this kind of symmetry on the lattice. So and then the most singular error terms, we have to encode them in the regularity structures. So we should lift this whole thing to the level of regularity structures. Not only the main terms equation, but also these remainder terms, and they renormalize each other, and so this means we have to look at a much larger regularity structure than the one used for the continuum Yang-Mills dynamic in 2D. So the regularity structure in continuum in 2D has only maybe 10 elements, right? You see the binary trees corresponding to the quadratic term in the equation, and this is cubic term, and you just iterate them to each other, get these trees. But discrete Yang-Mills in 2D, we have to introduce many more new elements. Okay, and actually we have the funny noises here, the square and so on. These are just noises multiplied by epsilon and so on. Okay, we view them as a new noise. Anyway, now, if we were in continuum, we have a general theorem called the BPG theorem, as Martin said, proved by AJ and Martin, which allow us to automatically renormalize and bound this elements. But now in discrete, we don't have an analog of this theorem. So we actually bound this, we renormalize bound these elements one by one by hand and see how they renormalize, how they affect the equation. But I want to say that actually it's not just the lack of black box theorem in discrete setting. The question really rather what should be a discrete black box theorem include, right? So you see, for these new elements in the discrete setting, it's not just the finite difference, not just replacing the heat kernel by discrete heat kernel. These elements, this object, they come with some factors of epsilon, and but we still need to renormalize them, even they have epsilon. And also, there are some symmetries which may or may not be preserved in the discrete level, right? And also, some of these guys, they are kind of non-local, and if you want to localize them, the localization may affect the symmetry and so on. There are a lot of issues here. So we hope that our, by hand calculation provides some, or shed some light, provide some good examples on, how to even formulate a general black box theorems. Suppose we, let's say, want to do three-dimensional result, right? So let me just summarize. So in 2D, as epsilon go to 0, we can show that the discrete dynamics converge to a limit, which is the solution to the continuum Yang-Mills equation with some renormalization, C. And this C is the sum of all the constants that we get from all those remainder terms, as well as the interaction between the remainder terms and the main terms in equation. So then there comes the question of identifying the limit. Is this limit really the same as the limit we constructed earlier, in continuum with AJ, Ilya, and Martin? In other words, is this C here we get here, right, the same C as the C in the earlier paper, which leads to a gauge covariant dynamic? In principle, all the constant C here from all these remainders, they're explicit. In principle, you could just try to sum them up, right? Maybe 50 or 100 of them, but we don't want to do this. Okay, we don't want to sum them and compare with the C in the continuum paper. We have a better argument that Ilya will tell you. This relies on better understanding of the continuum equation. The key is to use the gauge covariance to characterize the limit in some sense. Okay, so finally, I guess this workshop is about the critical dimensions, just some remark. So our result in 2D, but in 3D, the continuum dynamic local solution and also gauge covariance were proved in another paper in another paper. But in 4D, the Yang-Mills model is critical, so there's no solution theory yet. But on a fixed lattice, in 3D, actually, yeah, in 3D and 4D, we can still derive the discrete equation. Okay, this is still possible. We can still derive the discrete equation in this form plus remainder terms. It's just that we can't take the limit now. So in 3D, in principle, the remainder terms become much more singular. So more remainder terms should be encoded in irregular structures. This really requires very general black box theory on the lattice. In 4D, the well-known issue is that these terms become critical. They have marginal dimension, marginal power counting. But not only that, there are actually infinite many remainder terms which also have marginal power countings. For example, these kind of remainder terms will show up. They all have power counting -3, which is the same as the main terms. This is a new, if you want to look at a discrete model, this is an extra difficulty. Okay, I'll stop here. Thank you.
Thank you very much. Is there questions? Yeah.
Hi, thanks for this talk. Can you hear me?
Yes.
Okay. So in four-dimensional lattice simulations, there's a lot of work in trying to find an improved action, one which approaches the continuum limit faster. Is there any comparable measure for your in your two-dimensional case that you can say which action approaches the continuum limit faster?
Faster, you mean as you take the lattice spacing to 0,
yes.
or as
Yes, as you take less. That would be called an improved action in the real world when you only have a finite amount of computing time. One that approaches the continuum limit faster is obviously more efficient. I wondered if there was any element of that in your study of those three different actions, for instance.
Yeah, that's a good question. I haven't thought about that, about the convergence rate. But one thing I can say is that among all the error terms, there's an error term which comes from our assumption on the action, right? We just assume the action is like a log square plus a remainder. I gave 3 examples. One is the Manton action, where this error term is just 0. So the Manton action is just defined to be that. Okay, so this term itself is already gauge invariant in some sense. So you can just define this as a model. So I don't know, presumably if that model just comes with no error, okay, at least as this error is 0, then maybe that's a good start. That I guess that's at this moment that's what I want.
Okay, thank you.